course instructor Pavitra GS, Assistant Professor, Department of ECE, Sai Vidya Institute of Technology. We will start with the second module, that is ARM instruction set. So in first module, we have learned the architecture of CORTEX M3 ARM processor, and also the main features of ARM processor CORTEX M3. And we have seen the functional blocks of ARM Cortex M3, and we have also studied different operating modes in ARM Cortex M3. So now, in order to program the Cortex M3 processor or microcontroller, we just have to learn the instruction set of particular processor. So today we will learn the instruction set of ARM Cortex M3. Before we start with the instruction set, we need to just know the data size and the available instruction set of the processor. Now the data size, as you already know that the ARM processor is a 32-bit processor. That means the data which it is capable of processing it will be 32. Hence ARM processor is a 32-bit architecture. So the first point here says that ARM processor is a 32-bit architecture. What do you mean by 32-bit architecture? It means that the data bus or the data on which the processor is processing, it is capable of operating the data of 32-bit size. Hence the name 32-bit architecture. And we have already seen that we have two instruction sets in the ARM processor. It is ARM instruction set and thumb instruction set. ARM instruction set is a 32-bit instruction set where single instruction will be represented in 32-bit format. Again, I'm stressing on this point. You please note, ARM instruction set is a representation of a single instruction in 32-bit format. Anyhow, the ARM processor will operate on 32-bit data. There is no doubt in that. But in ARM instruction set, the representation of single instruction will be 32-bit. Whereas in thumb instruction set, no doubt it will operate on a 32-bit data. Here also, it will operate on a 32-bit data. But the representation of single instruction will be 16-bit here. Now, you will have a question, why you are representing a single instruction in 32-bit as well as in 16-bit. It is obvious answer that in 32-bit representation of instruction, it requires more space for storage. Whereas the same instruction, if it is compressed into 16-bit and then it is stored, then the memory space will be reduced. So hence we have two types of instruction set, ARM instruction set and thumb instruction set, that is 16-bit thumb instruction set, 32-bit thumb instruction set. You know that thumb instruction set is the subset of ARM instruction set. So that is what we have given here. The thumb instruction set consists of 16-bit instructions that acts as, here the 16-bit instructions means that it is compressed form. Okay, just for the storage purpose, it is a compressed form. Whereas ARM is a 32-bit instruction set. So you have to remember, whenever I say thumb, it is not that it is operating on 16-bit data, it is operating on 32-bit data, but the storage space for each instruction will be compressed to 16-bit just to reduce the space in the memory. Next, we will see the registers available in Cortex M3. So the registers available in Cortex M3, we have totally 37 registers. Out of 37, only 32-bit 30 general purpose registers are available for us. So again, we have already seen the registers available which are accessible to the user, that is from R0 to R15. Each register, that is total 37 register, out of 37 register, each register length will be 32-bit. Each register will be 32-bit. Now let us see what are the registers we are going to use and in the programming. So out of 37, we are not using all 37 registers. Only for the user purpose, we have only few registers accessible. So let us see what those are. The first one is a program counter. you already know what is a program counter. So we have one program counter. What's the length of program counter again here? It is a 32-bit register. Next, we have a program status register. So we know that program status register again can be APSR, CPSR, and SPSR. APSR is Application Program Status Register. CPSR is Current Program Status Register. SPSR is Saved Program Status Register. The format or the register status we have already discussed in the module 1, APSR, CPSR, and SPSR. All these registers are of 32-bit registers. Now we have general purpose register, that is in 30 number. So we have 30 general purpose registers. Out of this, we are not using all 30. We are using only few that is accessible by the user. So now, what is the use of current program status register and saved program status register? So current program status register reflects the operation, that is arithmetic and logical operation done by the user. So that will be reflected here. Saved program status register will be used when an exception is called, or when we execute a call instruction. So then saved program status register comes into picture. We have two modes. We have already studied two modes and two levels. So we have now user mode and the privileged mode. It is clear that in user mode, the normal program execution will be done, whereas in privileged mode, exceptions will be handled. That is, ISRs will be executed in privileged mode. So we have user mode and we have privileged mode. Now let us see what are the registers available in user mode and what are registers available in privileged mode. So we have a set of 15 registers R0 to R15, so which is available for accessing in the user mode. That is R0 to R12 register. We have R13, that is stack pointer. R13 is also called as a stack pointer. R14 is also called as a link register. So link register holds the return address during call instructions or during ISR executions or exception handling. So link register holds the return address. Now the next register is program counter. Program counter is referred as R15 or PC. Program counter is referred as R15 or PC. Next, only in the user mode, we cannot access the other PSRs. We can access only current program status register. So PSR is nothing but a flag register where all the arithmetic and logical operations will be reflected on this. That is CPSR, current program status register. Next, we have second mode as privileged mode. You already know in privileged mode, we can only handle the exceptions during interrupts. So we have that is system mode. In system mode, we cannot have this privileged mode. So here in privileged mode, we have access only to saved program status register, not CPSR, not current program status register. We have only access to SPSR, that is saved program status register. Anyhow, these two will be seen in a figure now as shown here. So this figure shows ARM versus thumb programmers model. So we have two instruction set as we have discussed. One is ARM instruction set, other one is thumb instruction set. What's the difference here? This represents the instruction in 32-bit, whereas in thumb instruction set, this represents, or this is a compressed form of 32-bit representation. That is 16-bit representation of single instruction. So from this figure, you can easily understand that whenever we are using ARM instruction set, then all R0 to R15 registers are accessible. R0 to R15 are accessible. And the only PSR which is accessible is CPSR. CPSR reflects the arithmetic and logical operations. Hence, this is accessible to the user. And whenever you are using thumb instruction set, that is the compressed form of ARM, then only the lower registers R0 to R7 are accessible by the user, not the higher registers. So along with the lower registers R0 to R7, we again have SP, that is stack pointer, link register LR, PC R15. So these registers are accessible in thumb mode. Now we will see which registers are accessible or available in different modes. We have different modes of operation in Cortex M3. So that is user mode, FIQ mode, SVC mode, abort mode, IRQ mode, and undefined mode. SVC mode is nothing but a supervisory mode. FIQ is fast interrupt mode. Abort mode, IRQ is interrupt request mode, and we have undefined mode. From this figure, that is register banking, we can see that in user mode, what are the registers available for user access? All R0 to R15 registers are accessible to the user along with only CPSR. And in FIQ mode, anyhow, we are not bothered about these modes because we are not using anyhow this, and this is not accessible by the user. But for your information, you just have to know what registers are being used in every mode here. Okay, this might be useful for your Viva. So in user mode, you have access to all the registers R0 to R15 along with current program status register. And in FIQ mode, you have access to that is user is not using all these registers. The processor have the access to higher registers, that is R8 to R14. And again, this is not using R15 register. So instead of current program status register in FIQ mode, which PSR is being accessed here? It is being accessed, that is the register being accessed is SPSR, that is saved program status register. One common observation you have to do here in this slide is in user mode you are using current program status register. In remaining all other modes you are using only SPSR. SPSR is being used. That means you should observe that only in user mode we are not executing the exceptions, that is ISRs is not being executed in the user, whereas in other modes whatever is given here, FIQ, supervisory, abort, IRQ, undefined, in all these modes we are going to execute the exceptions, that is ISRs. Therefore these are being used for handling the interrupts. Hence, the PSR which is being used by these modes are only the saved program status register, not the other two PSRs, that is APSR and CPSR. They are not using APSR and CPSR, only SPSR is being used. In the remaining four modes, that is SVC, abort, IRQ, and undefined, you can see only two registers are being used, that is R13 and R14. So you just remember in user mode what are the registers being used. That's all. That's very important as of now. Now this is very important, ARM instruction set. Now we will start with the exact instruction set. Whatever we have studied till now is just the prerequisite, just for having some basic knowledge before we start with the ARM instruction set. Please concentrate on this. This is very important for your examinations, and especially the load and store instructions. Now let's see the features of ARM instruction set. The first feature of ARM instruction set is load and store architecture. load and store architecture. Already you know the meaning of load and store architecture. So I'll repeat what is load and store architecture. Now, suppose if you have data in the memory and that memory data has to be processed. So in normal processor or normal microcontroller, the data in the memory can be directly processed. But whereas in ARM instructions, ARM processor, the data in the memory cannot be directly processed. Please note this point. The data in the memory cannot be processed directly. Instead, whatever the data you are interested in processing has to be loaded into the register. Then you have to process in the register, then store back into the memory. Hence, this process is called as load and store architecture. I will repeat this again. The data in the memory cannot be processed directly in ARM processors. Hence, the data in which you are interested in processing has to be loaded into the register, processed in the register, then stored back again in the memory. So this process of loading data from the memory, processing the data and storing back to the memory is termed as load and store architecture. So the second feature is conditional execution. This feature is very, very important, and we have much advantages for having this feature in ARM instruction set. That is conditional execution. In conditional execution, I'll explain you what is conditional execution with a simple example. So we have one example, compare R0, R1. So you already know what's the operation of this instruction. It compares the contents of R0 register with R1 register. Compare R0 content with R1 register. So what can be the results? Results can be either greater than, less than, or equal to. Now after the comparison, you have immediate instruction add ne. So usually you have seen only add instruction, add mnemonic, but conditional execution helps you to include condition in any instruction of ARM instruction set. Like you can include the conditions in move instruction, subtract instruction, logical instruction, data transfer instructions, and comparison instruction, all other instructions. So you can have a conditional along with the mnemonic, whichever the mnemonic present in the instruction set. Now let us see the operation of this instruction. The first instruction compares the contents of register R0 with contents of R1 register. Now here, now assume that if you have not used NE here, it would have been add R6, R5, R4. So here you can have three operand fields where we have used R4, R5 and R6 registers. And R6, all these registers are 32-bit registers. Now without NE, the operation would be the contents of R4 will be added with R5 and the result will be stored in R6. Now you have a condition included here. NE represents not equal. So when you have a conditional execution, it just compares the content of R0 with R1. The contents of R0 with R1 will be compared. When these two contents are not equal, then only addition will be performed. Otherwise, it will execute the next instruction. If they are equal, it will go to the next instruction. If they are not equal, then only this instruction will be executed and it performs addition of R4 and R5. Result will be stored in R6 register. That is the destination register. So this is very important feature in ARM instruction set. The first important feature is load and store architecture, which means that you can process the data only in the registers, not in the memory. Hence, we have load and store architecture. And second important feature is conditional execution, where you can include conditions for any instructions available in the ARM. And the third feature is load store multiple registers. So there's one more advantage here. There is a requirement of storing and loading multiple registers at a time, which saves the execution time of an instruction. So multiple registers can be loaded, multiple registers can be stored back to the memory. We have one more important feature here. And you already know shift and ALU operation in single clock execution. The major advantage in ARM processor, ARM Cortex M3 processor is all the instructions will be executed in a single clock cycle. That is, all ALU operations or shift operations, even these operations are executed in a single clock cycle. So these are the four very important features of ARM instruction set. I hope everyone have understood these four features. Okay, we'll move on to the next one. As we have discussed that in user mode, we have only CPSR, which is accessible to the user. Now let us see what is CPSR. How does it look like? The format of CPSR. I told you that PSR just reflects the arithmetic and logical operations of whatever the user is being done in the program. So it just reflects the result of arithmetic and logical operation. So in current program status register, that is CPSR, we have it is totally of 32-bit register. In 32-bit register, only CPSR is defined for the uppermost 4 bits. That is from 28 to 31, N, Z, C, and V. N stands for negative flag bit, and Z stands for 0 flag bit, and C stands for carry flag bit, V stands for overflow flag bit. So we have 4 flag bits defined in CPSR. Now, I already told you that we have 32-bit ARM instruction set and 16-bit thumb instruction set. This is one simple example of coding the instruction set. So it is a ARM instruction set where instruction is encoded in 32-bit data. So you need not remember this. This is just to make you understand that after you write the instruction, how it will be encoded in 32 bits. So this is one simple example of encoding each instruction in 32 bit. Now let's see similar examples. So this slide shows you the different types of instructions in which it is encoded in its own way. So you have the instruction type here. So instruction type, the data processing instruction, multiply instruction, long multiply. So we will study all these instructions one by one. You just have to know that for every instruction, the encoding will be different. Okay, that is what is required from this slide. You need not remember all this. This is just for your information. That is how every instruction is being encoded into 32-bit. Similarly, the same instructions you are using, but in thumb, how many will be defined? Only 16 bits encoding will be done, not 32 bit. In thumb instruction set, the same instructions will be encoded into 16 bit, not 32 bit. That is what you have to note from this example. Next, we will start with the first classification of the instruction. So in memory access instruction, only two instructions are defined, that is load and store. So load and store are the only two instructions defined in memory access instruction. Already we have seen what is load. What is load? Load is loading data from memory to register. Please remember these two. It's very important. Load means storing from memory to register. Store means storing the data from register to the memory. Load from memory to register. Store from register to memory. Now, what you're actually loading and storing? You are loading and storing the data. How many bits of data you are loading and storing? It is actually 32-bit data because you are working on 32-bit processor, hence it is a 32-bit data. Now these 32-bit data can again be divided into the different uh, types of data. That is, one is byte. Byte refers to 8 bits. So you can have 32-bit data into different bytes. So byte refers to 8 bit. Then you have half word. Half word refers to 16 bit. And we have word. Word refers to 32 bit. So we have three data types here. It can operate on byte, and it can operate on half word, it can operate on word. So load is from memory to register, store is from register to memory. It can be used for both signed and unsigned data. It can support for both signed and unsigned data. And you cannot perform on memory to memory data transfer. This is very important. You do not have instructions for moving the data, loading or storing data between memory to memory. That is not possible or supported in ARM Cortex M3, because the important feature you have already learned is load and store architecture. That means it does not include memory to memory data processing. Now let us see the different examples or mnemonics for load instructions. So first we will learn the load instruction, then we'll go for store instructions. Load, again, whenever I say load, you have to remember from memory to the register. Now let's have one simple example. So these are the different load instructions. Let us first learn here, and then we'll go for the examples. The mnemonic here is LDR. LDR is load word. Word refers to 32-bit. So how many bit data will be loaded from memory to register? 32-bit data will be loaded from memory to register. Next you have LDRH. H refers to half word. So this means only the 16-bit data will be loaded from memory to register. LDRH is load half word, which refers to 16-bit data. Next you have LDRSH, load signed half word. So it is now referring to the signed data. Signed 16-bit data you are loading from memory to register. Next you have LDRB. B refers to byte. That means you are loading 8-bit data from memory to register. Similarly, you have option for loading the signed byte. LDRSB, load signed byte. You are loading signed 8 bits from memory to register. Now we will see this later in the examples. It is similar to load operation, but the data is being moved from register to memory. Store is from register to memory. So similarly, you have STR, STRH, which refers to half word, STRSH, store signed half word, STRB, store byte, STRSB, store signed byte.